Welcome to Hartman Math. Today we're going to take a look at conic sections and in particular parabolas within a conic section perspective. So we kind of take a look, and when we're talking about cones in an algebra sense, we're talking about what's called a double napped cone, which means it's got the cone on top and on the bottom. And unlike a cone in geometry, it doesn't truly have a base. It just keeps going forever and ever in both of those directions. So the ones that we're going to kind of study here are the non-degenerate cases. The degenerate cases are if we have our cone and we slice it. That's so when we talk about sections, that's the slicing. If we slice right through the center, we're going to intersect at a point. If we slice right along an edge, we're going to get a line. And then if we slice straight down, perpendicular to the theoretical basis, and it passes through the center, then we're going to get two intersecting lines. But the ones that we're going to be focused on are when we actually pass through the cone itself. So the one that we're not going to really do a whole lot with the circle, but if we slice it parallel to the base, we're going to get a circle. So we have our cone, and we slice it parallel to the theoretical base, we're going to get a circle. If we slice at an angle and it passes through one of the sections, then we're going to get an ellipse. And the one that we're going to talk about today is if we slice through and it passes through the base, then we're going to get a parabola. And later we'll talk about if we kind of slice it straight down, don't pass through the center, then we're going to get a hyperbola. And there are two parts to that called two branches. We're going to focus on parabola today. And so this is our general form equation for our conic sections. Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Now, for our purposes in this class, we're going to always have the capital B be 0. So that kind of wipes out that term. If B is not 0, what happens is it takes any of our conic sections, like our parabola, and in the plane, it tilts it. So it's at an angle. It definitely complicates things quite a bit. So we're really not going to go to that level. So we're going to have our B be 0. And then if we're talking about a parabola, then that's going to mean also that A or C is equal to 0. So our parabolas are going to have x squared but not y squared, or vice versa. The ones that are functions, you've probably studied in other classes, Math 2, Math 3, and so on. The ones that are functions, there's no y squared. So if it's x squared, we have a parabola that opens up or down, that's fine. We're going to see if there's no x squared but we have y squared, those are going to open parabolas to the side. So not functions don't pass the vertical line test. So our definition in terms of a conic section of a parabola, it's all these points that are equidistant from a fixed line called the directrix and a point that's always going to be on the axis of symmetry called the focus. So the vertex is the same distance away from both. This point here, this distance and this distance are the same. This point here, this distance and this distance. Over here, if we were to go distance and distance, remember when we go to a line, it's a perpendicular distance. So all those points that are equidistant or the same distance from both of those points. And that kind of drives the work that we're going to do. Okay. Our standard equation in terms of conic sections are going to be for the normal opens up or opens down, x minus h squared, because I think that's kind of the one that we're familiar with from the past. When x is squared, opens up or down. So x minus h squared is equal to 4 times p, talk about what p means, times y minus k. The vertex is h comma k. So that's going to have a vertical axis, opens up or down. If it opens to the side, y minus k, notice that k always goes with the y. Y minus k squared is equal to 4 times p times x minus h. So it's going to open to the sides. If we're lucky enough where the vertex is the origin, we get 0 and 0. It just becomes these. But this is what you want to know. Okay. P is a directed distance. Directed distance from the vertex to the focus. If you go up, P is positive. If you go right, P is positive. If you go down, P is negative. If you go left, P is negative. So it's a directed distance. Be mindful of whether it should be positive or negative. That's the P value. So 4 times P, that's in the problem. So it just gives you an idea. If it opens down, the directed, this distance, you go from there to there, that's P, it would be less than 0. We're going from the vertex to the focus, we went right, P is positive. Example number 1, find the standard form of the equation of the parabola with vertex 1, 3 and focus -1, 3. So it probably makes sense to kind of have a sketch. Get some graph paper. This would be really helpful because we can get a lot of information from the sketch. So we've got a vertex. At 1, 3. And a focus at -1, 3. So we got to decide, is our parabola going to be of the horizontal or vertical style? And when we talk about that, we're talking about the axis of symmetry. Well, our points line up horizontally, so it's going to be horizontal, which is our not normal one, which means that there's going to be the y that's being squared. Y minus k squared is equal to 4 times p times x minus h. We were told the vertex, so we got the h and the k. H is 1, k is 3. P, it's easiest to get it here. We can get it algebraically, but it's easiest to get from here. Go from the vertex to the focus. How far, what direction? 2 units, we went left, it's -2. This is how to get it algebraically, which ties into coordinates here. But then you have to memorize instead of visualizing what's going on. We went left 2, p is -2. So that's going to go there. We've got our h and our k. There's our equation. All right, then graph it. We kind of got the sketch there. But probably a good idea just to do the whole thing on graph paper here. We've already got our vertex and our focus. Next is the directrix. Okay, so if from the vertex we go left 2 to get to the focus, we're going to go right 2 to get to the directrix. In this case, since our axis is horizontal, our directrix is going to be vertical. So x equals 3, since the vertex has to be halfway in between both of those. So if we went 2 to the left to get to the focus, 2 to the right takes us to the directrix. So we've got that. Now, we need 2 more points for our parabola, and we're going to do it based off the definition that all the points have to be the same distance away from focus and directrix. So we're going to ask ourselves this question. How far is it from the focus to the directrix? It is 4. So now, from the focus, we're going to go 4 units. In this case, up and down. 4 up and 4 down. Because those points will be 4 away here and 4 away there. And they satisfy the definition for a parabola. So those points have to be on if they're the same distance away. So we need our parabola to go through these 2 points and the vertex. Don't forget to put arrows. There's our graph. Included the vertex and these other 2 points generated by points that are this distance away from both focus and directrix. 4 units, so we went up 4 and down 4 for the graph. All right, checkpoint. Go ahead and pause the video here until you come up with the equation based on our information as well as the graph. All right, so if we kind of look at plotting the vertex and the focus, we can see they line up vertically. So that's our usual parabola, x being squared, x minus h squared is equal to 4 times p times y minus k. And then the vertex gave us the h and the k. So that's going to go here and here. We just need to find the p to get from the vertex to the focus. We went down 1, so p is -1. That goes here. 4 times -1 right there. And that's our standard form for parabolas in terms of conic sections. Okay. The graph, besides those points, since this distance is 2, we go 2 left, 2 right, and there's our parabola. Example number 3, find the focus. Well, this is kind of in the old style, y equals ax squared plus bx plus c. That's not that useful for us. We wanted to get into this new standard form of x minus h squared equals 4 times p times y minus k. So we're going to want to probably complete the square to do that, to get it into that something being squared form. And I definitely don't like the 3 here, so maybe we just multiply everything by 3. And I want to complete the square over here, so I'm going to kind of ignore this here for just a second. Focus on x squared minus 6x, and I want to complete the square there. So take the -6 divided by 2, square that, we get 9. So I really want this to be plus 9. To get from plus 3 to plus 9, I'll just add 6 to both sides. All right, then I can write this as a square, x minus 3 squared. Over here, I need it in that form 4 times p times, so whatever the leading coefficient is, you have to factor it out. Even if that was a 5 and you say 3 is not the common factor, doesn't matter. You have to factor out whatever is the leading coefficient there. So we're going to factor out the 3. It's kind of reversed here. There's our standard form. So from that, what we know is, I know the vertex. Vertex is 3, -2. I can also find the p, because the p is going to take me from the vertex to the focus. From our equation, that's 4p. Always in front is 4p. So 4p equals 3. I can write that equation, and I can solve for p. P is 3/4. So I know my vertex is 3, -2, and from there, I want to go up 3/4 from 3, -2, and that's going to take me to, because this is vertical, it's going to take me to 3, -2 plus 3/4, because I'm going up, which means my focus is at 3, -5/4. 3, -5/4. Now, it didn't ask for it, but what if we needed to instead, or also, find the directrix? Well, it's the same thing. Instead of going up 3/4, I'm going to go down 3/4 from the vertex, and that's going to take me there. In this case, it's going to be, since our axis is vertical, our directrix is going to be horizontal, and it's going to be 3/4 below -2. So y equals -11/4 would be the directrix if we needed to find it. So one of the things about parabolas have a lot of applications in the real world, and one is in terms of reflecting light. So we might be talking about like headlights, where there's the lamp to it and it's shining back on a mirrored source, which allows it to focus and then send everything out in a beam like this. All right, reflective properties of parabolas. So what it's saying here is that if we have a tangent line, meaning that the line here touches, just kind of rests up against the parabola, intersects it at exactly one point right there. So if we have a tangent line, that tangent line is going to make equal angles with, so tangent line, and if we draw from that tangent point to the focus, that angle and the angle between the tangent line and the axis of symmetry, they are going to be the same. Which means, if we were looking at this in terms of a triangle, because it has two angles that are congruent, it would be an isosceles triangle. That's going to help us in the next problem. So, isosceles, that tells us this distance and that distance also have to be equal. So example number 4, find the tangent line, or the equation of the tangent line, at a point on the parabola where, pretty basic parabola, y equals x squared, the most basic parabola, and we want the tangent line to have a point of tangency at 1, 1. So let's just kind of maybe start with a sketch of the idea. Number 1, find p. Well, it's not exactly, I mean, I guess it is in our form, the x being squared here. So if we look at it in terms of, obviously this tells us the vertex is 0, 0. So x squared equals 4 times p times y. So since this is a 1y, 4p has to equal 1. So p is 1/4. Now let's sketch. Here's our parabola. Passes through 1, 1. Vertex is the origin. Since p is 1/4, that tells us if we go up 1/4, we're going to reach the focus. Well, we can see based off that last diagram that if we make a triangle out of here, this angle and this angle are congruent. And that means that this length and this length are congruent. I think we should find those lengths. Because we're trying to write the equation of the tangent line, we need a couple things. We need to know what's the y-coordinate for this point right here that's on the y-axis. So let's start with this. Let's find the distance. Let's do the distance formula between these 2 points. So distance would be the square root of, or distance squared is the squares of those. We would get 25/16 by doing the distance formula. That's distance squared. So if we square root that, we're going to get the distance 5/4. That distance is 5/4, which means that this distance is also 5/4. So what is 5/4 lower than 1/4? That tells us that the y-coordinate here is -1. So 0, -1, there's our y-intercept. Now we can find the slope of that segment, that tangent line, using there. So you can use the slope formula, find the slope. We get the slope is 2, y-intercept is -1, y equals mx plus b, equation of the tangent line, y equals 2x minus 1. So there's a lot involved. We had to find a lot. We had to do distance, we had to do the slope, find the slope, all that kind of stuff. In calculus, when you do this, when you get to calculus, and you learn some other techniques, it turns from maybe a 10-minute problem, 5 if we're really quick about it, into maybe a 20-second problem, maybe 15 seconds is how fast we could do it using calculus. We're going to have to learn that at a later time. But that's it for today. I'll see you next time.